gave a version of this talk in Nagoya 6 months ago, so this is in some sense incremental. So one of the things, of course, for solar heliospheric and ionospheric is the instantaneous UV coverage of the MWA device, which is unique for solar work because the sun is so variable both temporally and spectrally. So you cannot use either multi-frequency synthesis or aperture rotation, Earth rotation synthesis. You have to make your images in half a second in a single frequency channel to do the science. So the MWA has a unique advantage over any other instrument on the planet for that mode. And that's the point. So there's been a number of really interesting new results, and I'll just do a bit of a grab bag of those. So one of the more interesting phenomena in the sun and the heliosphere is coronal mass ejections, because they have very meaningful impacts on the near-Earth environment in particular, in terms of the radiation environment for astronauts, in terms of the disturbances it induces in the ionosphere, geomagnetic storms, power surges in power grids, and things of that nature. So understanding these things is a high priority. And low-frequency radio astronomy is a really good way to get a handle on some aspects of the behavior of these things. So what you see here is work done by Patrick McCauley, and this is a time sequence of images. There's extreme ultraviolet imagery from AIA, in this case 204 angstroms. MWA 80 megahertz is the blue contours, and this stuff here is white light coronagraph imagery that shows Thomson scattering from the electrons in the CME. And what you can see here in the UV image is a disturbance heading out from the far side of the sun, but in that general direction, and it is associated with this radio feature. And then sometime later, the CME, which is directed somewhat away from us, starts to show up outside the coronagraph disk here as a bright white signal that is associated with the shock front of the CME being driven into the corona. And what's unique about this is that there's radio emission associated, apparently spatially coincident with the shock front. This is not what is normally seen. It's thought to be gyrosynchrone emission. This is actually, a few minutes later, you can see this at several different frequencies. So you have some spectral information about it. It looks for all the world like it's gyrosynchrone emission. But up to now, the only instances of this type of radio emission associated with the CME has been from the core of the CME, which is a rarefied region behind the shock front where there's strong magnetic fields. And so this is the interesting thing. It's a new phenomenon, or seems to be a new phenomenon. And what really one needs is the maximum possible dynamic range of imagery so you can track this sort of phenomenon as far out into the heliosphere as we can. So this is a rather interesting new piece of science that's emerging now. This is a bit of an elaboration of something that I presented in Nagoya 6 months ago. And it relies on high dynamic range MWA imaging. Again, this is a unique capability that the MWA has, which allows us to make detailed spectral measurements of the more traditional type of radio emission that has been seen from CMEs. That's from that core region of the CME, over a range of locations and across a broad frequency range. And because of the dynamic range imaging, the bottom contour here is 0.02% of the peak. So this is tens of thousands to one dynamic range. And you can, this is just one image at one frequency, at one instant. But there's actually measurements that could be made at the location of each of these blue circles, and a couple of them are shown as an example here of the kind of spectral coverage you get from that, and so you can diagnose the properties of the gyrosynchrone emission in a really quite a comprehensive way. For reference, all of these other plots are the sum total of spectral information on these things from other instruments over the past decade or more. It's interesting because one of the more difficult things to get at in the solar corona is the magnetic field, this configuration of strength, and this emission actually helps you trace some of that. And one thing to note is that we are only scratching the surface at the moment, trying to skim the cream of the large amount of solar data that's been taken to date. There are a very large number of interesting events that are in the can that we haven't got around to looking at yet. And I'll come back to that point a little bit later. This is something that I showed before. This is again work by Patrick McCauley at the University of Sydney. And he's done a really nice job of doing a simple but effective polarimetric calibration for circular polarization. And almost all of the polarization that you see from the sun is circular. The Faraday depolarization for linear is extreme in almost all circumstances. But the circular polarization is really very interesting. So just to recap the way that this calibration is done, it relies on the assumption that most of the pixels in an image will have very low circular polarization. So you just adjust the calibration until you get the maximum number of pixels with zero net circular polarization. And when you do that, this is uncorrected, and when you do that simple-minded correction, you get really quite nice high-fidelity polarimetric information. And this has been used to do a variety of scientific investigations. He has a very nice, fairly comprehensive paper. I'm not sure what stage it's in. It's either submitted or I'm not sure whether it's published yet. But there's a number of interesting phenomena that can be discerned in circular polarization. This is an example of the circular polarization signature of coronal holes, which is a little bit unexpected. There is a ring of one sense of circular polarization and then the opposite circular polarization in the middle. And from the physics of the situation, it's actually a little bit hard to understand. I don't know whether you've made progress on that. But this is throughout all of the solar data. You can do this really quite straightforwardly. Huge amount of information. This is another one that I showed a little bit last time. Then there are type 3 solar bursts, and these are caused by jets of electrons accelerated typically in magnetic reconnection events. They travel out at a large fraction of the speed of light along magnetic field lines, and as they travel out, they cause radiation at the local plasma frequency or a harmonic of the local plasma frequency. So as they propagate out and as the density decreases, the frequency of emission drops. That's why you see type 3 solar bursts sweeping down in frequency with time. And this happens over timescales of seconds. So here you see, taking that to the next level, where you have imagery of this type 3 emission. And as the blob of emission associated with the type 3 moves out, it also moves down in frequency, as you can see here. And by looking in more detail at exactly how the spot size increases, how the velocity goes, you can get a tracer of the coronal density as a function of height. And you also have to fold in questions about whether the ray paths are being refracted. So are these things actually where you think where they appear to be, or are they actually coming from somewhere else? So that's another research topic that continues to be very active. Talking about type 3s, they do complicated things because the field lines are complicated. So this is an example of a type 3 burst imaged with the MWA. No other instrument can do this, where the field lines actually split. There's a closed loop and then there's an open field line. And the electrons stream out along both these things and separate out, and you end up with these bimodal structures at the lower frequencies, further out. Lower frequency equals further out, lower density. And also, there's a really interesting phenomenon that I think this is actually published now. There's quasi-periodic oscillations in type 3 radio emission, but until images were available, that could not be associated with other properties of the type 3 phenomenon. It turns out that the angular size of these type 3 features oscillates along with the flux density and not in obvious ways. And that is good evidence that whatever's causing the oscillation is not happening locally where the type 3 emission is occurring, but down much deeper in the corona where the triggering mechanism for the type 3 emission in the first place is happening, and that's where the oscillations are being generated. So this is all quite new science enabled by the ability of the MWA to do imaging as opposed to just measuring the total intensity. So taking this a little bit further, there are lots, I've mentioned this many times before, there's lots of weak burst type non-thermal emission on the sun wherever you look, whenever you look. And in some respects these bursts, which are very short in time duration and somewhat narrow in frequency extent, they bear a lot of similarities to type 3 bursts. If you look deeper, you find that they're going on all over the place. But this is looking at the whole sun. You can do better than that. We'll skip that one. So this is a really interesting observation that the group in India, led by Divya, this is actually Atul Mohan, who's led this particular piece of work, and they have been able to use what they call spreads, the spatially resolved dynamic spectrum. And what that does is it takes a single pixel of the MWA image and produces a dynamic spectrum just of that location on the sun. This is something that you're not able to do with other instruments. So zooming in on one particular feature observed in the in the extreme ultraviolet, 12,000 kilometers across, and looking at the dynamic spectrum just of that spot on the sun, you find that these weak non-thermal features have a really striking periodicity. And this is seen a little bit more clearly. This is the time period here of greatest interest. And there's a really striking 30-second periodicity in the intensity of these features. They come and they go and they come and they go, and there's a 30-second thing. It does appear that these things are somewhat like type 3s generated by particle jets of some kind. Again, the conclusion is that the periodicity that's being observed is actually intrinsic to the production mechanism of those jets. There's actually some sign of weak periodicity before this event of this X-ray flare and the associated magnetic loop were noted. So this is still, so it's a very interesting phenomenon. I'm not sure that, I haven't actually read the paper yet, but as far as physical interpretation, it poses a number of interesting questions. Another thing that's an indication of the type of research that is going on right now with MWA data. So again, looking at an active region where we have other information that tells us roughly what the magnetic geometry is in the corona. We have information on the location of magnetic loops, and more specifically, we have information on where spatially those magnetic loops reach a height that would produce emission at a given frequency. Remember, height translates to frequency of emission. It turns out that for this particular, these are type 3s, for these particular emissions, you predict that the low frequency stuff would be where these red squares are, because that's where those magnetic field lines reach that height. The 165 megahertz ones would be the green squares, and the high frequency, nearly 300 megahertz ones, would be down here. And the shaded regions are where the MWA actually sees those emissions, and they're really not very well correlated. The emission is not coming really from where you expect it to come from. Also, the size of these blobs is quite a lot bigger than you expect to see. And what this is telling you is that the propagation effects through the coronal medium are very strong. They're causing refraction, and it's not just a radial density gradient that's doing that. There are transverse density gradients as well, possibly ducting, and certainly scattering that broadens out the angular extent of the emission. So that's unfortunate if you want to do a close connection between what's happening along these magnetic field lines, but it's really interesting if you want to learn about the corona itself in terms of its propagation properties. Am I doing on time? 2 minutes, oh God. Type 3 studies, this has been shown before. We're able to do just position measurements of spots of emission, and for type 2 radio emission, you can make really spectacular high-resolution pictures of where the emission is coming from, and this is the size of the MWA beam, so that's much smaller than that. Wide field IPS measurements, this has been seen many times. These are examples of the type of science you can do. This is the background polarized sky, which is the galactic tinplon radiation modulated by Faraday rotation in the stellar medium. It's strong, it's everywhere, and you can measure Faraday rotation against it in the heliosphere. So if there's a CME running across, you might expect to see a signature of that CME in Faraday rotation propagating like that. So I put together this little chart that shows what aspects of instrument performance pertain to the various different types of science. And rather than go through all of these squares, which would take longer than 2 minutes, or 1 minute now, I imagine, note that the one thing that everybody needs is precision calibration. And the calibration is limited right now by small-scale structure in the ionosphere. So this is evidence of small-scale structure in the ionosphere, these wiggles correlated between adjacent antennas here. That's very small-scale stuff happening on tens of seconds. It's just a few degrees of phase at 150 megahertz. This wasn't really understood until the MWA came on. It's the same stuff that causes ionospheric scintillation, that's LOFAR data. So what's actually happening here is you've got a turbulent, mixed-up ionospheric layer that introduces a phase front from any one direction, but we look from different parts of the solar disk, which is about a degree across at these frequencies, you see different phase fronts. And that's a difficult problem, a difficult calibration problem. You have to, first of all, figure out how to parameterize this phase screen using Zernica polynomials or similar, and then you have to propagate your model through that ionosphere in order to compare it with the measured data so that you can close a cell-cal-like loop. And we're in the process of trying to do that in a pipeline. This is where you would do that work. It's in progress. One of the things we really want to do is generate a solar image database. Imaging the sun is actually a tricky business. It's an enormous amount of data. So what we need to do is those data are not much use to researchers, but for the solar community. So what we want to do is set up the pipeline and crunch through a significant amount of data. I think it's plausible in the near future to do something like 10% of the available data, which would allow us to sample a large range of the phenomena that are buried in those data. This is a computing cluster actually used for VLBI correlation at Haystack Observatory, and we only use about 30% of it because the VLBI data is episodic, and the remaining time amounts to about 6 million CPU hours a year. So one of the plans here is to put that to use and create a resource for this very high information content, high SNR, for machine learning and machine-assisted discovery in the form of a massive image database. These are the SHI publications in the last 12 months. Those are the ones that are in referee journals already. These are the ones that are under review. That includes the big science paper, but there's solar science in there as well. And these are in preparation. So quite a lot of science output from this group. So these are the future goals. They're pretty much the same as what I showed in Nagoya. It doesn't mean that we're not making progress. It just means that we haven't made so much progress that the goals have completely changed. That's it.
We have time for a couple of questions. Colin? Sure. Just regarding the image database. I think I talked to you about this last meeting, I think, but at one stage LOFAR was creating one of those as well. Just wondering if there's value in, having a multi-facility image database.
There might be if there are some aspects of solar imagery that LOFAR can produce that the MWA cannot. But LOFAR does not have the kind of UV coverage on relevant scales. I mean, we're fairly close to the scattering limit, the coronal scattering limit, with the MWA resolution and the extended duration. So the longer low-power baselines are going to start resolving everything out, you would expect. There may be some exceptions because of ducting and so on. But by and large, the interesting stuff is revealed by very high dynamic range. And that low-power cannot do. It just doesn't have the coverage. There may be complementary aspects, but I think this database would be the state of the art sometime to come if we were able to generate it.
That's a quick one. So the weak non-thermal images that was treated about 30 weeks.
Yes.
Presumably, looking at the pixels that have different, is there like a spectrum? Like, is there other limits to the fastest and slowest you've seen?
Well, you're asking me if I've seen it.
Well, no, sorry.
I'm going to need to ask Divya and his group about that. But certainly the stuff that I've seen, this looks like quite a unique piece of data that we've looked at the moment. I mean, there's many interesting events that can be zoomed in on, revealed by AI imagery or X-ray flare events. But they've just chosen to zoom in on one or two with the MWA, where the MWA has to be observing. There's masses of data. We can probably look at many instances of this, and that would be a very interesting parameter to explore.
Let's thank Colin again.